I circled them because there was some miscommunication within the audience. I heard different answers. And those different answers, well, clearly one of them was wrong. Okay? So the answers are currently up there. Let's make sure I didn't make any typos. I went through and did that. As you guys shouted out numbers, it confused me. Yeah, all those are good. Okay, so the number written next to those in red is the number of SigFigs. So let's take a look at number 2. Okay, number 2 only has 2 significant digits. We apply the rules that we've given. The numbers 1 through 9, or the digits 1 through 9, are always significant. Okay, so what I like to do is underline them when they're significant. To decide if that 0 is significant, I have to then follow the subcategories. And we've got 2 sub-rules that come out of that. Okay? It's all dependent on a decimal point. Okay? So for that number, there's no decimal point, so I follow rule 2. Okay? The 0 must be controlled by numbers to the left and to the right, and officially by significant digits to the left and to the right for it to be considered significant. So what we would do is start at that 0 and look to the left, and what do we have? A 2. Okay? I think you can do better than 2. A significant digit. That's what's to the left of it. How about to the right? Nothing. Which then means it is not a significant digit. Only 2 significant digits there. The 0 doesn't count. Okay? Why does question 3 all of a sudden jump up to 3 then? I do have a decimal point, which means the rule changes. If there is a decimal point, all I need is a significant digit in front of it. What was the 2? Significant digit. So that 0 now becomes significant. Make sense? Okay, 4. Again, I have a decimal point. The 1 and the 2 again are significant. Take a look at my first 0 on the left. I look to the left. What do I have? A significant digit, so the 0 is significant. All right, I move to the next 0. I look to the left. What do I have? A significant digit. Yes, it is 0, but I've already established it as a significant digit, which means that last 0 is also significant for significant digits. Make sense? Okay, it looks like we're moving to 7. Again, a decimal point. The 1 and the 2 are, again, always significant. We take a look at our first left. Thank you for at least acknowledging it. Our first 0, and we look to its left, what do we have? Nothing. Okay? For 0 to be significant, it must be preceded by a significant digit. There isn't one, which means not significant. We move to the next 0. We look to its left. What do we have?
Not significant.
A not significant 0. Insignificant sounds kind of mean. Okay. So we have 1 and 2, 2 significant digits in 7. How about 8? Those first 2 zeros will again not be significant because there's nothing to the left of them. No significant digit to the left of them. The 1 and the 2 are valid. What's the deal with the last 0? It's preceded by a significant digit, which then means it is significant. All right, so we end up with 3 in that last one. Does that make sense? All right, 3 rules. That's it. All right. You might encounter some other rules where they talk about ambiguous zeros. Okay, what they're really saying by that is that nobody knows because you didn't follow rules. Follow the rules and then it's not ambiguous. Okay? These 3 rules is all you really need. Okay? What's the difference between 5 and 6? Just for giggles. Just the leading 0. Okay? You might ask, well, why do I care about that leading 0? It's not significant, right?
It would be if it was a 10.
Okay, it would be if it was a 10. Okay, that's true. What number did I just write? Okay, Wolf, can you see right there? Mm-hmm. What is that?
A point?
There's a point. When most of us take a decimal point, it becomes very difficult to see, particularly if we just stab at the screen. Okay? for those of us look really, really closely inside that little box, there's a dot, which means that number's not 12, it's actually 0.12. Is 12 significantly different than 0.12? Yes. If I had instead written, why the hell would I write 012? That doesn't make any sense. Oh, I probably wrote the 0 because I meant a decimal point is embedded in there. By including that leading 0, it holds no significance as far as your significant digits, but it does draw your attention to, hey, maybe you meant to draw a decimal point. That's the only reason it should be included. Make sense? So, aesthetic reasons. You don't have me for lab, so you don't have to worry about it, but you will typically see me, when I grade something, circle a number like that and write LZ next to it. For
Lazy.
Well, it is kind of lazy, actually. Leading 0. I don't take off points for it, but I'm just trying to draw your attention that it is very simple to make that typo and turn that number from 0.12 to 12. Okay? And I guarantee everybody in here is like, I will never make that mistake. You will in one case, on the exam when it matters. Okay? So just show the leading 0, it simplifies things. Okay? Questions about those rules? Why do we have these rules? Make sure you don't fail, not quite. The rules actually go all the way back to, keep going, oh my gosh, our measurements. When we're in the lab, we tend to stress less about significant digits because we take measurements. The instrument tells us what our significant digits are. We just read it off the instrument and we're done. So we don't have to worry about it. What's the problem with the lecture? You don't have measurements. The only measurements you have are what's given to you, so you need to be able to interpret that data according to the significant digits. And we might say, well, still, who really cares? Does it make that big of a difference? Okay? Yes, which we'll see in just 1 second. Okay? Measurements versus exact. Okay? How many quarters do you see there? Those are quarters, right? Yeah. 7. How many significant digits in that?
Well, in the value or in the quantity?
It depends on what we're measuring.
It's not one significant digit, because by saying one significant digit, you're saying 7.1. Okay? 7.0. Well, how about 7.01?
Why are you naming the 1?
Okay? We don't know what that digit is. By saying only one significant digit, you're saying you don't know what the next decimal is. Okay? What that next value is. That's what your measurement means. So if I say 7, then I'm saying I don't know what the 10th place is. Well, you do. You do know what the 10th place is. It's 0. So maybe it's 7.0, but then how many SigFigs would I have? 2. Do you know what the next decimal is?
Yes.
Yeah, you know it's?
0.
0. So 7.0 isn't valid. 7.00 is now more valid because we know it's 7. But then you would keep continuing. Well, where do you stop? That's going to really suck to have to write out the measurement of 7 quarters being 7.0000, right? You're going to fill a page with zeros. I wish we had a better way of representing this. We could go through with a line. Scientific notation actually doesn't fix it either. Is it a measurement or is it an exact value? It's an exact value. Measurements carry SigFigs. Exact values do have SigFigs, but the value for your SigFigs is infinite. Okay? Which means when we deal with exact measurements, okay, or exact observations, we can ignore the SigFigs altogether in our calculation. Okay? For instance, let's take a look at another one. Let's see if I can be a decent artist. Oof, maybe I'm a horrible artist. Hey, there we go. Not that bad of an artist. I have a foot.
You drew it with a hammer toe, but
Yeah. No, isn't that more like this?
It's an 8.
How many inches in that foot?
12.
What's the SigFigs? Okay. It's an infinite amount of SigFigs. There are exactly 12 inches in 1 foot. Okay. There's not one SigFig because of 1 foot. There's not 2 SigFigs because of 12 inches. There is an exact value, which means I have an infinite number of SigFigs. Kind of makes sense? Okay. So remember that when you go through and take exact measurements. Right? They officially aren't measurements because you aren't using a device per se. It's a count typically. Okay. So why do we worry about SigFigs? Okay. Really what's going to happen with our SigFigs is when we move into operations. Just looking at the number of SigFigs for any individual value is pretty meaningless. There isn't a reason to do it. The reason we make you do it is so that we know that you understand SigFigs, so that when you then move into mathematical operations of addition, subtraction, you can apply your SigFigs accordingly. If we take a look at the calculation here, okay, we add that up. We pull out the calculator. What does the calculator tell us our answer is? Okay. If I've done my math right, I think 1,5. See, I'm so good I can add this up in the non-standard direction. There we go, right? I'm awesome. That's what our calculator spits out as an answer. Is that the correct answer? No, that answer is wrong. But didn't my calculator tell me that was the correct answer? Yeah, but your calculator doesn't understand SigFigs. Right? The correct answer is actually just those. Right, well, now why? Well, if we follow the rules, our result is only as precise as the least precise measurement. Right? Which of those values is the least precise? The top one only goes to the tenths place, which means when I do my addition, I'll run it standard in the calculator and I'll look at it, but I can only report out to that precision. Everything after that, I don't know anything about. But again, let's go to the far right, isn't 2 plus 0 plus 0 equal to 2? Why can't I report that 2 then?
because you can't assume that after the 3 is just zeros.
Is that a 0 in the previous calculation? No, we have no clue. We have zero concept of any precision there. That could be a 0. It could also be a 9. And if we go through and do the math now, do we end up with a difference in our additions? Yeah. That difference turns out to be significant. How did we discover that was significant? Unfortunately, we probably discovered it was significant because somebody died. Okay? So when we're running our calculations, we have to be aware of the precision of our measurements. Right? And we have to track that through our calculations. So when we're doing addition and subtraction, we can only report our answer to the least precise measurement. Well, that's not too bad, right? Everybody okay with that? Right. What happens if we do a different operation? How about multiplication and division? What is the area of that? I know it's not a square. I should probably fix that at some point. What is the area of that rectangle? Okay, so our area was 7.28, whatever our units are, times 4.6 units. Okay. I didn't cheat this time. I actually don't know what that answer is, so I'll just advance. 33.488 units squared is the answer our calculator spits out. What answer do we have to report? Okay. I heard 33.4, which would be great if this was an addition-subtraction calculation. Is it? No. What is our rule for multiplication and division? The fewest number of SigFigs. How many SigFigs in 4.6? How many SigFigs in 7.28? 3, which means my answer can only get reported to 2 SigFigs. How do I convert the number of 33.488 into 2 SigFigs? Okay. And I end up with just 33. For those of you doing 34, you're adding a rounding step into it, which we haven't gotten to yet. Okay. If we looked at 33.4, is that closer to 33 or 34? 33, we keep it at 33. Okay. Officially units squared. Does that make sense?
So if it was 5 or above, it would be 34.
We'll account that in a couple slides. Okay. Again, why do we have to go through and do this? Okay. In our first calculation, we're assuming, or the calculator's assuming, that is 4.60. Okay. And the next one, what if that, instead of it being a 0, was a 9? Okay. Does that change your answer? Yes. Okay. So we have to be careful when we manipulate our SigFigs to ensure that the result is as accurate as the measurements that calculated from, or that we calculate afterwards. Does that make sense? So just follow the rules for SigFigs. You have to do that. Okay. How big of an issue is calculating SigFigs for the sake of the class? Not really. No one's going to die. You might lose some points. Okay. But if we think back to how we would have to write a question involving SigFigs, that means I'd have 4 or 5 answers that all have the same numbers but varying numbers of SigFigs, right? Which means whatever I asked in the question as a calculation, if it had any science content, I'm not testing on that science content. The only thing I can test on would be SigFigs. So when you go through and look at the practice exam, how many people have looked at the practice exam yet? Good. Okay, for the next exam, that is, not the past one. Okay. When you go through and look at that, you will be able to call attention fairly quickly to questions that are about SigFigs. Because you'll look at your answer choices, and they will all be the same number with varying numbers of SigFigs. Okay? That is really the only time you see that question. It may appear to have a bunch of other calculations involved within it, but it's relatively straightforward. You just have to evaluate how do you apply your SigFig rules. Make sense? Okay, I think I saw maybe a hand. No. Okay. Okay. What if rounding? Okay, so if we go through and look at these calculations, I change the number slightly. When we look at the addition subtraction, I can report out to the least precise place, which in this case is which place? The hundredths place. Okay, and I would end up with 1.33. I look at that last, or the first insignificant digit. Okay, that's 5, which means I'm sitting right smack dab in the middle between 1.33 and 1.34. How do I decide where to put that number? Should it be 3.3 or 3.4?
3.3.
The general rule
For now, we're putting the 5.
goes up.
Everybody comes up with a general rule. Unfortunately, that general rule, depending on who you talk to, sometimes changes. Okay? The rule that we run with is 5 or greater, you round up. Which means since I have a 5, I will add 1 to the previous digit. My number becomes 1.34 grams. Okay? What about the other question, our multiplication and division? Okay, we can only report out to 2 SigFigs, so that's 36. Okay. 5 is the first insignificant digit. That number is 5 or larger, so I will have to add 1, and it becomes 37 units squared. Make sense? That's how we'll apply rounding. Okay? Again, it is not consistent to make an added further wrinkle to this depending on where those numbers get sourced from. Okay? It's a chemistry class. Those numbers will very likely be atomic masses. Okay? When we go through and look at our periodic table on the wall here, we have reported out to, what is that, tenths, hundredths, thousandths, 10,000s? Is that counting the right place? To the 10,000s place. Does your textbook report out to the 10,000s place? No. And you'll notice even on this periodic table, not all of them report out to the 10,000ths place. They report out to different locations, which means if you decide to include all of those numbers in your calculation, your number is slightly different than the number that I use, right? Just slightly different from what the textbook used. Where does that slight difference tend to fall? Right into the rounding error, and you can end up being ever so slightly off based off of those numbers. So be careful when you look at questions both in the textbook, practice exams, your actual exam, all of that. Okay? SigFigs is something that we have to be cognizant of. We have to be aware of this rounding effect and realize it is applied very inconsistently. Okay? I tend to be aware of that inconsistency, and so when I write questions, I make sure that I don't have on the test 36.5 and 36.4, okay, when I'm looking for 37. Okay, so we'll apply those rules very carefully to make sure that you don't have two answer choices that potentially line up. Does that make sense? Okay. That said, let's pause. So with that bright, happy note, let's move forward. Okay. So there's our rounding. Always round at the end of a calculation. If you have to do 20 calculations, you do not round. You carry as many significant digits through as possible, or as many digits through as possible. At the very end of all of those calculations is when you round. And only then. Okay? You guys want some practice with it? See what you can come up with? I heard a yeah, so let's go ahead and do that. Looking through those, does anybody want to challenge and be like, but wait? Nobody? Everybody's like, no, those are all good. Okay, thank you. Which question?
Number 3.
Number 3.
Yeah, because my calculations that I put in says 129.068. So I'm not sure where the 129.04 comes from.
Can I get a confirmation on that? Could easily be I entered in the calculator wrong.
I think I have a confirmation.
I got 0.04.
Yeah, I got 29.041,
0.04.
so yeah.
Okay, so what I would recommend you do is check your calculation again.
Okay.
Okay, and this is something that is frustrating. Within science classes, not only do you have to know the science content, you have to be able to run the calculations, and then you actually have to be able to input those calculations into the calculator correctly. Any typo along the way, everything goes to crap. Okay? So this is why I would recommend you always check your work and write out your work, because then you finish the exam early, you go back, you run the calculation again. Do you get the same answer? If you get the same answer, then sure, you're probably right. Okay? Or you're at least right in your calculation. You haven't made an entry mistake. Okay? But everybody was okay to reporting out to that place? 3.09 only has 3 SigFigs. Number 3. 3.09 only has 3 SigFigs.
So that means that your answer can only have 3 SigFigs. No, just because.
No.
The reason I'm calling that out is for this very reason. It's very easy to get confused between the two operations. This is addition, subtraction. I don't care how many SigFigs is in my measurements. What I care about is
The least precise.
the least precise place. The least precise place is the hundredths place. That's the important part, not the number of SigFigs, which means my answer gets reported out to the hundredths place. What happened in this calculation? I started with 3 SigFigs and I end with 5. Guess what can happen in addition, subtraction, or addition?
You get more significant.
You can get more SigFigs. Guess what happens with subtraction? You can end up with less. For instance, take a look at question 5. How many SigFigs in your answer?
Oh, I actually got that right.
1. Only 1 significant digit in your answer for question 5.
That's hard with it.
And yet we started with 4 and 6. How did we lose so many SigFigs? The difference between those numbers was not large enough for us to see enough significant digits come out. And so we end up only saying 1. This is why when we do differences, which you will do in the lab, you've already done in the lab. We try to make sure that we get large differences in our measurements, because when we subtract, what's going to happen to the number of SigFigs? They can disappear. Okay? Since we want our measurement to hold as many SigFigs as possible, we try to get the largest differences. You all did the density lab, right? Okay. How many of you were spot on the density for your metal? Okay, 2 people. Why were you so far off? They gave you a very tiny piece of metal. When you put that tiny piece of metal into the graduated cylinder with the water, what happened to the volume? It changed, but it changed by a very small amount because the volume of your metal was so tiny, which then means you can't see that difference well. You get a very tiny difference in the volume. Your result comes out to be horribly inaccurate because your volume was inaccurate. Okay? So we aim for large differences when we look at subtraction. What happened with question number 4? 3.09 only has 3 SigFigs, so we have to have 3 SigFigs in our answer. Where's that number? 4540, what your calculator spit out? No, what did it spit out?
4538.
0.47 is what I got.
So your calculator spits that out. Why do I lose so many digits? Well, I can only hold 3 SigFigs. Okay? Mistake number 2 that very typically happens. It says, oh, I can only hold 3 SigFigs, so it's 454. This is your paycheck. Started at $4,538 and it just became $454. That kind of sucks. Okay? So we have to make sure that we don't lose the meaning of where those numbers were located. The 4 needs to be in the thousands place. To do that, I can place a 0 as a placeholder to force the numbers further forward. The instant I put a decimal point, though, the 0 now becomes a significant digit, not a placeholder, and my answer is wrong. Right? Make sense? So we have to be very careful in how we report our answers to ensure that we don't add meaning or lose meaning from our calculations. Last one on 6. Should have gotten 454. The biggest deal I wanted to address there was this units. We can't cancel those units. So we don't. I have grams in the numerator, I have centimeters cubed in the denominator. That's it. They don't disappear. What is the number in front of centimeters cubed? Okay. I heard a 0. Go ahead and do that calculation for me. 0.0454 divided by 0. Your calculator freaks out. You can't run that calculation. Okay? So, what number do I put there? There's an implied 1. If it is anything other than 1, what happens to the 0.0454? It becomes something different. So I can do a multiplication and division, kind of ignoring the units, and just do the math, okay, to get a number. That number will then go typically in the numerator, depending on what you're looking for, but it's typically written in the numerator. The number written in the denominator will be 1s to make sure that you don't change the meaning of it. Make sense?
How significant is the question at the bottom?
How important are SigFigs? This is really, really important for scientists and engineers. For you in this class, not that big of a deal. It'll be relatively straightforward. You'll see it in the exam questions that you're being asked for SigFigs. Do you have to take 151 and 152? Then don't stress about it. Get through this class. If you do have to take 151 and 152, significant digits are much more important. You'll have to keep going back to it and keep getting kind of beaten over the head with them. Okay? So I think it's nice to put it all on one slide. Unfortunately, I animated the slide. So we've got our significant digit rules at the top, how we deal with addition, subtraction, multiplication, division, and then our rounding. All conveniently zeroed in on one slide, which you could take a picture of, perfectly all right. You could also have downloaded the slides and just print out that one slide. Okay. Fine with me, I don't really care, but it's there. Okay. Do we want anybody else taking pictures before I move on? Okay. that puts us at nomenclature. So for future record, if you want to go back and review SigFigs, there's a couple places you can go. Number one, we have that lecture. The first 30 minutes of today's lecture is all recorded, SigFigs. You can go back and look at it. It is also in a play pause it quiz that I can get you access to. It's intended to match the lab, but that's up to you. Okay? The next big part is nomenclature. Okay? In theory, most people went through and watched the nomenclature video. Okay? Play pause it sometimes gives you issues. If it gives you issues, contact me and I can get you some workarounds. I have gone through with all the quizzes. Right? And in that quiz, it says it gives you the link to the play pauser, right? The very bottom of that, it also gives you a link to YouTube. Right? All of the videos are already stashed on YouTube. It can suck to sort through and find at least mine. Right? So I've got a link there for the YouTube that the play pause it is based off of. Yes, Randy.
On the they downloaded the slides, is the rest of the stuff just crossed out?
So if you downloaded the slides, I do apologize. I realized that the nomenclature wasn't put in at the right section, so I slid this slide forward. If you check maybe 10 slides later, you'll find this slide.
Yeah, okay.
Yeah. The rest of that content is important. We will get back to it. I don't know if we'll get back to it today.
The text on this nomenclature read like stereo instructions, but the play posit was super clear about it, but the text just didn't do it.
So nomenclature, and this is one of the reasons why it's all shifted online. You'll notice that for nomenclature I have one slide, arguably two there, 3 slides, oh, and then no more slides. That's because I find nomenclature abhorrently boring, okay, and relatively meaningless. Okay? We can't say entirely meaningless. Okay? My personal experience, nomenclature is something that continues all the way through all of chemistry. It shows up in organic chemistry too. I had to withdraw from OChem because I was failing it. When I went back and took it, there was one section that I said I'm not going to bother with. It was nomenclature. It was 10% of my grade. I ended up with an 89.5% in the class. Okay? Kind of sucked because that was a B. Okay? SigFigs be damned, right? Okay? So nomenclature is important. People test on it at differing levels, but it's ultimately a rule. If you know the rule, it's trivial. If you don't know the rule, it's impossible. Okay? Just think about the names of every person in this classroom. How many of you know the names of everybody in here? I'm not even sure I can raise my hand on that because I screwed up at least 3 people. I apologize. I'm working on it. Okay? It's not easy to know those because they're relatively arbitrary. We, within science, have tried to build rules so that it makes more sense, okay? But that's about it. Okay? They're weak, approximate rules. Okay? The video tries to outline all of those rules. Unfortunately, it outlines all of those rules in a single video, so it is an hour long. Okay? Your textbook outlines all of those rules and throws a bunch of extra stuff in there because, I don't know, they did. Okay? Because why not, I guess? The tutoring center. Has somebody gone to the tutoring center yet? So, we'll probably do this a couple times through the semester. What I will go through and do, in theory, relatively silently, because I have to think about it. Because again, it was one of those things I just decided to ignore, so I'm not the greatest at it. And I will write down everything that I would try and do for a test. Okay? Or say a quiz in your lab. Eventually. Right? So this is what I'm given. I want to work from it. So how do I start?
Find the cat.
And for those of you looking at this, you may say, well, didn't you write something wrong? Yes. Yes, I did. But by putting some information down, I can get some points. Okay. So, simple information first. Some quick adjustments. Yeah, question marks, because yes, I don't know that. Don't tell anybody I told you that. Oh, fun. 2x. What was I solving for? Charge. I didn't see what time I started that, but now I'm done. Okay? Questions about how I worked through and did that? Okay. What question do you have?
Can we go through it together?
Oh yeah, we can absolutely go through it together. Yeah. Okay. So what I'm going to now do, because you saw my process on going through and solving that. Okay. So I'm going to erase everything and we're going to do it all over again. Or rather, I'm going to do it all over again because I have a feeling you weren't copying me. Okay. So let's clear it all. So the first thing that I went through and did is identified whatever information I knew outright. So if we just focus on the first one, Cr is chromium. O is oxygen. You'll notice that I did write oxygen first. It's in a compound, so I can't call it oxygen. Okay? Not only is it in a compound, it's also at the end of my compound. So it's not oxygen, it must be changed to oxide. Okay? The last element in that sequence, okay, if we're looking at a binary compound, just two elements, we'll always have the ending change, the suffix change to "ide", always. Okay? So I have chromium oxide. The next part before I push further into this is deciding what kind of compound am I looking at. Okay? Well, what kind of bond is there between chromium and oxygen? Well, chromium's a metal. Oxygen is a nonmetal, which means I now have an ionic bond. Okay? So I need to be following the rule set for ionic compounds. Okay? But there's two rule sets. There's ternary and binary. Okay? Binary meaning two. How many elements do I have?
Two.
Aren't there five? There's 5 atoms. There are 2 elements. Because there's only 2 elements, this gets called a binary ionic. I now have to follow the rule sets for my binary ionic system. When we go through and look at the binary ionic system, the charge now needs to get added into the name. So the amounts, 2 chromiums and 3 oxygens, is a side effect, if you will, of the charge of the elements in the name or in the compound. Okay? So that charge needs to get reflected in the name. Okay? To do that, I have to realize that if I add up the charge of all of the elements in there, the compound will have an overall 0 charge. Should it always be 0? No. Should this compound always be 0? Yes. How do you know that?
Because there's no indicator of a different charge.
Upper right-hand corner, it doesn't show a charge. That means the charge is 0. That's how it works. So if I add up the charge for each of the chromiums, okay, so I have a charge that says charge chromium plus the charge of the next chromium. You do not have to copy this. Charge oxygen plus charge oxygen. Jimmy, Christmas. I can't believe I started this. Oxygen. Right? If I add all of those up, I counted for every single element, that has to equal 0. I want to simplify my calculation a little bit. Okay? Well, there's 2 chromiums. So I can take 2 times the charge on chromium plus 3 times the charge on oxygen. This goes through to give me a 0. Right? So it simplifies my calculation. So when we're running our calculations, it's the number of the element times its charge plus the number of the element times its charge plus the number of the element times its charge, and so on and so forth until you've counted for all elements. That must equal what?
0.
No,
The charge.
the overall charge. In this case, it is 0. Okay? So, do I know the charge on chromium? Well, we could go back to Wednesday's lecture and look at that handy-dandy little image that showed all the charges of all the elements that we were required to memorize. And if you looked at that, you would find chromium is not listed. You don't know what it is. You have to figure it out.
So X is.
What about the charge on the oxygen? That is one you are required to know. You either have it outright memorized, or you realize you need to know your nonmetals and your first and some columns and specificities off of that. Oxygen was a -2. So we end up with 2 times some unknown value plus 3 times -2 must equal 0. That was the 2x minus 6 equals 0. 2x equals 6. X equals
So chromium.
3. Okay? As I did it, you may have even heard me mumble, for those of you that were close. What did I say X was? I didn't remember. I have to remember back to what I was looking at. X was referencing the charge of the chromium. That's what I was trying to find. So I need to specify the charge of the chromium now in my name. That gets written as a Roman numeral right after the element, chromium-3 oxide. And that's it. That only took like 3/4 of that screen. Okay. Some of this you will pick up with practice and internalize. You will find most of the tutors can probably do this internally. I can theoretically do it internally. Okay. Oftentimes I know that I screw it up because it is a weakness of mine. I will try and write it out.
Why isn't the charge next to the oxide, if the charge next to the chromium?
Good question. Why did I not write chromium-3 oxide 2, right? Why?
Because the IDE.
So IDE tells us that it's part of the name. It tells us that it is charged. Why do I not specify the 2?
Because it's understood.
Isn't it because oxygen has a single charge that we should already know?
So there's the biggest answer, or there's 2 big answers to this. Number 1, oxygen always has a -2 charge. If it always has it, don't write it. Okay? Even if if it's not wrong. Sorry, as I mumble myself through that. NaCl, we could name that as sodium 1 chloride. What does that Roman numeral mean? Sodium has a +1 charge. Is that invalid? No. Is that the wrong name? Yes, you lose all credit. I don't make up the rules. Right? If you supply extra information, even if it's wrong or correct, your answer is still wrong. You can only supply what is immediately necessary for the name. Sodium 1 chloride is wrong. Okay? For the oxide, I know the oxide is always a -2 for the sake of this class. Okay? So oxide should never be written. What's the second reason the oxide should never get written for its charge?
What's written?
When do we specify charges in our binary ionic compounds? Only for the cation. Our metals. Is oxide a cation? No. Is it a metal? No. So when we look at that charge, the oxide isn't a +2, it's a -2. By writing a 2 there, it could become ambiguous. I could throw in the mathematical symbol of a minus, but it makes things even worse. Okay? So we will never include that charge for the nonmetal. Okay? Make sense? Enough? Okay. Is there another one in particular that you would like me to see or do? I mean, not see, but do? What's that? I heard someone say something. No. The lead one. Whoops. So let's take a look at the lead one. Again, when I went through to name, the first thing I did, write out the symbols. Lead, and then you saw me write C2H3O2. You should already know the symbol for lead being Pb. Acetate, is that one of our elements? No. How do you know that it's C2H3O2? You are required to memorize it. Right? So as an extra step within nomenclature, not only do you have to memorize the four, did anybody actually count how many elements you needed to memorize? 40-something? Okay, 40-something elements that you had to memorize the name on, their charge, if you were required to memorize the charge, and the symbol. You now have some other things that you have to memorize. Okay? You have to memorize their name, acetate. You have to memorize their formula, aka their symbol. And you also have to memorize the charge.
Is there a negative on that O?
I'm going to come back to that. Okay. I have not specified yet the charge on any of these. What this species is known as, acetate, is a complex ion or a polyatomic anion. Okay. There's a whole slew of them out in the world. Your textbook listed 20, 18? It was pretty close with 20. Okay. You should memorize those. Are you going to see all of those? If you do the homework, yes, you probably will see all of them. Okay. Do you expect to see all of them on an exam? Probably not. Probably the ones you're going to get tested on are the ones that your instructor thinks are the most important to memorize. That's why in the nomenclature video, what did I do? I starred several of them. 7? 7. So let's see if I can do it. Acetate, definitely one of them. Nitrate, sulfate, cyanide, hydroxide, carbonate, good call. Thank you. Hydrogen carbonate? That's 7 already.
Yeah, there were 7.
Oh, that was 7. Okay. Okay. Oh, hydrogen sulfate? Yeah. Okay. I don't even remember which ones I told you to memorize because I think I have them all memorized. Right? So I just tried to star the really important ones because I think those ones show up much more frequently. You should commit those to memory. Okay? Those will be the ones that I will put on a test. Okay? So, back to the problem at hand. Paul noted something. If we looked at acetate, they typically write acetate with a minus in the upper right-hand corner, specifying the charge on acetate. Okay? Remember, this is now a complex ion. That is a unit that goes as one thing. That minus charge now applies to that entire piece. Okay? The issue I have with writing that right now, do I have acetate?
No, because you're
No, what do I have? Yes.
lead acetate.
I have lead for acetate. I do not have acetate. I do not want to write the charge in the upper right-hand corner right now because that's now saying my lead acetate has a charge there. It does not. Okay? So where do I want to write that charge? Well, I want to write it where it's someplace useful for me. I will use it as a calculation later on underneath it. So I will specify my charge below. Okay? That is only because what I'm trying to do is make the compound. By including the charge there, okay, it can make your name incorrect depending again on who's grading. Multiple choice, probably not a big deal because you won't see it. Okay, so we'll come back to what it would look like if we'd included those charges and address why it looks confusing. Okay? What else do I know by looking at that name?
It's a metal.
Lead is a metal. Acetate is not. So I'm looking at ionic. For it to be binary, it can only have 2 elements. How many elements do we have? It has a lot more than 2. So it is ternary, ionic. Okay, really the only difference between ternary and binary is that we have that complex ion. It doesn't really change any of the rest of the rules. Okay? So in that, what does the Roman numeral then mean?
There are 4 bytes. 4 charges on lead.
It is the charge on lead. When I go through to build this compound, I have to make sure that it has a 0 overall charge. Well, that one becomes trickier. Why is it a 0 overall charge?
Balance.
2 ways to look at it. Number 1, whenever we're giving you a name and expecting you to draw a formula, we're expecting you to provide the neutral compound. So that's the number 1 thing. How would we specify or change the name so that you knew you were writing down an ion? I would add the word ion at the end of it. Now I know I'm looking at the ion. Which charge of that ion is it? I don't know. That's why I don't ask it. Okay? So we are assuming that when I add up all of the individual elements that went into this formula, that I get an overall charge of 0. -1 is for the acetate and the acetate alone.
No, everything goes to 0.
Okay? Everything for this compound must go to 0. Okay? So I need some number of acetates. I don't know. Let's pick Y. Plus some number of leads. Let's pick X. I also don't know. When I went through and solved this, did anybody see me write X and Y?
No.
No. Why not?
X is smart.
How do you solve this equation?
It's hard.
1 equation, 2 unknowns. Technically,
Answer one of the unknowns.
it is unsolvable. Okay? We have a set possible number. We have a solution set that would work to solve this, but we technically don't know. When we go through to solve our formulas, we have to use the smallest whole number ratio. So that means the values for X and Y will be
Whole numbers.
whole numbers and
Greater than 0.
small, because it's the smallest whole number ratio. Right? So when I went through and looked at this, I said, well, I think that's trivial. If X is 1, 4 times 1 is 1, minus Y equals to 0. This says 4 equals positive Y. I did it in my head. Okay? What if you can't do it in your head?
Sucks. Calculator.
Then you do what I just did right now. You write it down. Okay? What did I do to do this? I said X equals 1. Did I have to say X equals 1? No. So let's erase that. Let's say Y equals 1. What happens?
1 times -1 equals
4x
-1.
minus, whoops. I said Y equaled 1, right? So 4x minus, pen, minus 1 equals 0, right? Thank you for telling me the answer. I apologize for not listening to you. If I go through to solve, what do I get? 4x equals 1, and I get x equals 1 over 4. We said smallest whole numbers. Is 1 over 4 a whole number? No. That's why it's a fraction. Which means my guess of y equaling 1 is
Not true.
wrong. So I try again. I started with y. Maybe I want to make x equal to 1. Maybe I should make x equal to 2, x equal to 3. Tons of possibilities to go through and test. Start with your smallest numbers. Pick 1 for x. See what happens. Does it solve? Great, you're done. Doesn't solve? Try 1 for y. Great, you're done. Oh, didn't solve? Make x equal to 2. Make y equal to 2. X equal to 3. Y equal to 3. Okay? And go through and test all the way through. For those of you shaking your head, that sounds like a lot of work. It isn't, because you usually stop at 1 or 2. Okay? And with enough practice, you'll be able to look at it and trivially say, well, that meant that when I went through and solved, let's be careful with what I erase, that if x was equal to 1, y must be equal to 4. That means, now back to what did x and y mean? The x was the, what about the lead? It was not the charge, it was the number of lead atoms. Where do I specify the number of atoms in my formula? A subscript right after it. Okay? How many acetates are there? 4. That's what the y meant. So I could put a 4 here. Okay? The 1 we can imply. So putting the 1 there now is one of those things. It's right, but it's wrong because
Too much information.
we don't want it. It's superfluous information. Fancy word there, by the way. And I could say this is my answer. So let's put it all together.
Don't you need to bracket
There would be
acetate?
24 oxygen.
24 oxygens, that doesn't make any sense. There's not 24 oxygens, there's 4 acetates. This is why we use parentheses to differentiate that. Okay? There aren't just arbitrary reasons for dropping these things in there. We have pretty solid understandings on why we want to do this. Whoops. Helps if you actually finish the formula, though.
Only slightly.
Make sense? Okay. So back to Paul's initial suggestion at the beginning, wanted to specify the charge for the acetate. Which means we should also specify the charge for the lead.
That seems excessive.
That now seems excessive. We're putting a bunch of extra information in there. Again, it's not that it's wrong, it's that it's too much. So we're trying to simplify that by not showing it. If you had boxed that as your final answer, there are lots of people that would be like, well, are you telling me that the lead is a +4, should have a +4 next to it in the formula? Well, if you are telling me that, you're wrong. What you were trying to show by putting the charge there was your work to getting to the answer. So as long as you differentiate your work from your answer, you're okay. I would argue I'm lazy. I want my work in a separate space, and I'll provide my final answer in the same space that I was working in. Everybody understand that? Make sense? Okay. Or sure is good enough. Okay. So when we go through and do nomenclature, we have to go through and classify our compounds and understand what we're looking at. So ionic and covalent are the biggest differences. We start with those two. Okay. Most people don't need any help with the covalent compounds because the covalent compounds are straightforward right out of the name. That one was nitrogen. That one was oxide. Because it's a covalent compound, 2 nonmetals, I do not specify charges. Why do I not specify charges?
Only specify modes.
It's not even you don't need them. That's actually technically wrong. They're sharing electrons. That's true, but why do I care? Why do I not specify the charge?
But not cations.
Because you're not losing or gaining any electrons.
So going back to the definition of them, we're not losing or gaining electrons. We don't have a cation. We don't have an anion. Okay. To have charge, you need to have an ionic compound. Is that an ionic compound? No. So we don't have charge. It is an invalid statement to even be looking at charge because there isn't. Okay? It's a covalent compound. There is no charge associated with it. Okay? The next part of it is specifying the amount because the charge doesn't allow me to figure out the amount of each element, so I have to specify the amount blatantly. 2, I will use a Greek prefix di. 5, I will use the Greek prefix, and this is the part that I don't remember. It's either pentoxide or pentaoxide. I don't know. It's one of those two. Pentaoxide sounds a little weird, so I would probably lean towards pentoxide, but I don't know. Okay? So in a case where I had to write down a name, that's exactly what I would do. I'd write it down with the parentheses and the question mark, saying that I'm acknowledging that I don't know, but I know sometimes it's important. And then I put it in the hands of the grader and be what may, that's what they decide. Okay? Tricarbon dioxide. Okay? Just the flip. I've got the carbon, I've got the oxygen. Tri is the Greek prefix for 3. I have 3 carbons. 2 oxygens, C3O2. And that's it. What's that? Interesting question. Notice for the dinitrogen pentoxide and the tricarbon dioxide, does anybody see anything about charge?
No.
No. Are those complex ions? No. Why are they not complex ions? There's no ion. There's no charge specified. If I wanted you to name them as a complex ion, what would we see? We would see a charge written in the upper right-hand corner. We aren't done, by the way. Carbon can do all sorts of weird charges in an ionic compound, not ionic. Let's see how well you guys were studying. Name of that compound. I heard a lot of people shout nitrate. And unfortunately, you're wrong, because that is not nitrogen or nitrate. That is nitrogen trioxide. What's the difference? There's no charge. For it to be nitrate, it must be charged. So nitrate is wrong in that case. It becomes nitrogen trioxide. Be very, very careful that you watch out for that charge. It can bite you.
So it would be nitrate if it had a...
If it had a -1 charge written in the upper right-hand corner. Okay? This was supposed to be a little bit larger. Do you want more? Clearly you don't want more right now. Okay?
Yes.
As far as practice the nomenclature goes, there isn't a whole lot for me to teach. It's just doing it. We can go through, I can incorporate a couple more of these kind of random picking 4 things and naming them in class. Do you guys want those in future classes?
Sure.
Yes.
Okay, we heard a yes, so we'll stick with that. I'll try and pick some harder ones. The next part of it, where am I going to get that practice? Because remember, I suck at nomenclature. I don't want to come up with my own compounds. In this document, this massive big document that looks an awful lot like your lab manual. There's an experiment with nomenclature. Okay? Do that now. Don't wait for the lab. If you finish it now, guess what? When lab happens,
You're done.
you turn it in. Drop the mic and walk out. Have fun.
Easy as possible.